section 11.6, just so you can see how this fits together. All right, so remember that we started off talking about the order of matrices, that like this one was a 3x4. We also talked about how you could label each individual number in the matrix as an entry. All right, so let's say that we have this system of equations right here. I could take out all the letters and just organize the numbers into a matrix. So if you'll notice, if I just take the numbers, I'm going to have for the first equation up here, that would be 1, -4, 3, 5. And look at the first row of your matrix, 1, -4, 3, 5. All right, same thing with the second row, -1, 3, -1, -3. And then same thing with the third row, 2, there's no y value, so that's 0y. So that would be 2, 0, -4, 6. So this is called an augmented matrix. And the augmented matrix is just your system without the letters in it, so that you can just focus on the numbers and getting them to getting your solution. Now, what would the order of our augmented matrix be? Rows and columns. What's my order? 3x4. Yes, so 3 rows and 4 columns. Now, if we took off just this last column, all right, because that was what was on the other side of the equal sign. You'll notice the little dotted line right here that kind of designates where the equal sign would go. So if I take off this last column and all I have left is this 3x3, what are all of those numbers? What do you call a number in front of a variable? Coefficient, right. So we call that the coefficient matrix. So if that last column is gone, what was on the other side of the equal sign, and all I'm left with is what was on the one side of the equal sign, then we call that our coefficient matrix. Now, that coefficient matrix, what's the order of that? 3x3. So a 3x3 or a 4x4 or a 5x5 or a 2x2, when the number of rows and columns are the same, we call that a square matrix. So when the number of rows and columns are the same, it's a square matrix. And then also remember, we talked just a moment ago about your main diagonal. Your main diagonal goes from first row, first column to last row, last column. So 1, 3, -4 would be in my main diagonal. So that's just some terminology that they will use moving forward with our matrices. All right, so look at example number 2. For example number 2, we want to write an augmented matrix for this system. Now, let me suggest to you that you rewrite that system first. Because if you'll notice, you've got X, Y, and Z in here. And so there's something missing in each one of the equations that I want to fill in. So for instance, on the first one, I've got 1x plus 3y, and I had no z. So I'm going to fill in a 0z for that one is equal to 9. All right, how about your second equation? What do you need to fill in? 0x, yeah. So I would have 0x minus 1y plus 4z is equal to -2. All right, now my last equation, I got all kinds of stuff going on because order is important. It does need to go X, Y, Z. So I'm missing a Y term, and this is not in the correct order. So how would I want to write my third equation? How many X's? 1x. How many Y's? 0y. And then we had the minus 5z. Okay, so now that I've rewritten my system, then I can write my augmented matrix. All right, so what's going to be in the first row of my augmented matrix? Perfect. 1, 3, 0, 9. How about my second row of my augmented matrix?
0, 4.
Uh-huh. And then our last row would be 1, 0, negative 5, 0. So we should be able to go either way with this. They should be able to give me the augmented matrix and me come up with the system. This is 1x plus 3y plus no z is equal to 9. Or they should be able to do as they did here, give me the system and me find the augmented matrix for it. Now, you might remember back when we were solving systems of 3 equations with 3 unknowns. We did it the Algebra 2 way. We took equations 1 and 2 and combined them and eliminated a variable. And then we took equation 2 and 3 and eliminated the same variable. And that gave us 2 new equations, 4 and 5. And then we solved that for a system. And then we back substituted all the way through. And it took like half a sheet of paper to do one problem, right? And they had told us at that point that another way of solving was to use Gaussian elimination. Gaussian elimination, named after Carl Friedrich Gauss, who kind of discovered the idea. And so for Gaussian elimination, I'm going to use elementary row operations to solve a system. What is an elementary row operation? Okay, there are 3 things that you can do with matrices that are row operations. The first one is you can switch any 2 rows in a matrix. Now, not columns, but rows. You can switch any 2 rows. Well, how can I do that? Like, how does that not change anything? Well, come over here and think about the system that's associated with that. Could you switch the second and third equation in that system? That wouldn't change anything, right? Doesn't make a difference if I call this number 2 and this number 3, or this number 2 and this number 3. It's the same system, right? So we can see why we would be able to switch 2 rows in the matrix as well. All right, the next thing that we can do is we can multiply a row by a constant. Okay, how can I just throw 2 into one row of the matrix and not mess it up? Well, come over and think about the system again. Over here on your system, can you multiply both sides of an equation by 2 in that system and not mess it up? Absolutely. We did that for elimination all the time, right? Like we would go through and we would multiply this by a positive 2, so we'd have a negative 2x and a positive 2x that would eliminate, right? So if I can do it to the equation, I can do it to the matrix. And then the third thing that I can do is I can multiply a row by something and add it to another row. So again, it's that idea over here where we took 2 times negative x and got a negative 2x so that we could add it to this other equation so that we could get them to drop out, right? So the same idea over here with my matrices, I can multiply a row by something and add it to another row. All right, so let's practice each of those row operations. I don't really think we need to practice switching 2 rows. That's pretty obvious. All right, but look at example 3C. They ask us to do negative 2 times row 1. All right, so let's take row 1, 1, 2, negative 4, 3, and let's just multiply it by negative 2. So negative 2 times 1, negative 2, negative 2 times 2, negative 4, I think we all know this. Negative 2 times negative 4, positive 8, and then negative 2 times 3, negative 6. All right, so that's how we multiply a row by a constant. All right, then the next thing that they ask us to do is they ask us to multiply a row by a constant and then add it to another row. Multiply a row by a constant and then add it to another row. So you can see over here, we're going to copy row 1 and 2 exactly as they are, but we're going to change row 3 because we're going to multiply negative 2 times row 1 and add that to row 3. It's going to change row 3. So we already did negative 2 times row 1 right up here. So we'll just bring that down and we'll add it to row number 3. So row number 3 was 2, 1, 5, negative 2. So again, here's our negative 2 times row 1. Here's our row 3. We're just going to add those together. All right, so negative 2 and 2, 0, negative 4 and 1, negative 3, 8 and 5, 13, 6, negative 6 and negative 2. So those are our 3 elementary row operations. The last thing we want to talk about today is row echelon form and reduced row echelon form, because we're giving ourselves all the tools and all the terminology that we're going to need to, in our next lesson, be able to solve a system using our matrices. All right, so row echelon form is when you have a matrix where the first non-zero number in every row is a 1. So first non-zero number is a 1, first non-zero number is a 1, first non-zero number is a 1. We call that a leading 1 because it's a 1 that's leading the numbers, right? The leading 1 in a higher row has to be further to the left than a leading 1 in a lower row. So you can see in the first row, the leading 1's further to the left than the second row, and in the second row, it's further to the left than the third row. So that is row echelon form. Now, look at this for just a second. What is the system that goes with this augmented matrix? It would be 1x plus 2y minus z is equal to 4. No x plus 1y plus no z is equal to 3. No x, no y, 1z is equal to negative 2. That's that little stair-step system that we solved a couple of sections back. It was so much easier to solve when it looked like that. So we're going to use these elementary row operations to transform whatever matrix they give us into row echelon form, and then it'll make that system so much easier to solve. All right, look at this second one right here. Is this in row echelon form? All right, is the first non-zero number in every row a 1? Yes. And is the leading 1 in the higher row further to the left than the lower row? Yeah, so it doesn't have to be just one stair step over like it was in that first one. As long as the leading 1 in the higher row is further to the left than the leading 1 in the lower row, then it's fine. All right, and then the last matrix over here introduces a row of zeros. So that's kind of strange. If you have a row of zeros in row echelon form, it has to be at the very bottom. So this row of zeros is at the very bottom. Is everything else true about this, that it's in row echelon form? Yeah, because every non-zero, the first non-zero number is a 1, and each leading 1 is further to the left than the right, than the one below it, and then all the zeros are in the bottom row. All right, look at this augmented matrix, this second one right here. And let's think about the system that would be associated with that. Look at your very last row and tell me what the solution to that system would be. So in your last row, you're going to get 0x plus 0y plus 0z is equal to 1. You're going to get 0 equals 1. What's the solution to that system? No solution, right? So that's what no solution looks like in matrices. All right, look at this last one over here that we were just talking about. And again, look at your last row. What would the solution to that system be? I'm going to have 0x plus 0y plus 0z is equal to 0. So I'm going to have 0 equals 0. What is that? Infinitely many solutions. So that's what it would look like. We have an example of one solution, no solution, and infinitely many solutions. Now, that's row echelon form. If I'm willing to do a few more elementary row operations, I can change this into something called reduced row echelon form. So if I go back to this very first matrix we worked with over here, if I was willing to do a few more row operations to transform this -1 and 4 into zeros, then it would give me reduced row echelon form that you see right here. Well, what's the big deal about reduced row echelon form? The only difference is above and below every leading one, you have all zeros. Above and below every leading one, you have all zeros. So that's why these had to change to zeros. Why is that helpful? What is the system associated with this augmented matrix? What's your first one? What's your first equation in this augmented matrix from row 1? X equals 4. That's 1x plus no y plus no z equals 4, right? That's x equals 4. What's the next one? Y equals 3. What's the last one? Z equals -2. Y'all, that's my answer right there, right? X, Y, Z. So that's how we're going to use matrices to solve systems. We're going to take whatever matrix they give us, and we're going to use elementary row operations to transform it into either row echelon form, where we could back substitute, or reduced row echelon form. All right. So now we have all the tools that we're going to need to do that process in our next lesson.